So welcome everyone. So our topic for today is a shear and moment in beams. So as you can see in the figure, so we have a figure of a beam which has a 12 meters long, and also we can see it is applied with a three different kinds of loading. So at point A, it is applied with a 50 kilonewton of a concentrated loading, while on point B to C, it is applied with a uniform type of loading with a 20 kilonewton per meter, and also from B to C it has a distance of 7 meters, while on C to D it is applied with a uniform varying type of loading with a 70 kilonewton per meter. So also, as you can see, the beam is pinned at point B, while on point C it is also has a roller at point C. So what we're going to do next is we're going to draw its load diagram. So the load diagram will be look like this. So the pin at point B, we replace it by a reaction force and name it as RB. And the roller at point C, we replace it by a reaction force and label it as RC. So since it from B to C, the load applied here is a uniform load, so we will get its forces and also its centroids same as from C to D, which it is a uniform varying type of loading. We will get its force and also its centroids. So first we're going to find its force. So to get its force is we'll just solve its area. So since it is rectangle, so its length times its height, so it has a 7 meter, and it has a height of 20 kilonewton per meter. Multiplied it, so 20. So 7 times 20, it has a 140 kilonewton. Since meter over meter is cancelled, so only kilonewton will be left. And also we will gonna solve its centroids. So to get its centroid, since it is a rectangular, we will just gonna divide its length by 2. So it has a length of 7 meters. So it will be now 3.5 meters. Well, in this uniform varying load, since to get the load is to get the force is just the area of that load, so the shape of this load is, since it is a triangle, so the area of a triangle is 1/2 times its base, which has a 4 meters, and its height is 70 kilonewton per meter. So 1/2 times 4 is 2, then 2 times 70 is 140, so we will get a 140, then meter over meter is cancelled, so kilonewton. So to get the centroids of this load, if we were going to start here to find its centroids, we were just gonna multiply its distance by 2 over 3. So 2 times 4 is 8 over 3 meter, or it's gonna be 2.67 meter. So that's their force for this load, and it has a centroids of 3.5. And so this force here, uniform varying load, it has a 140 kilonewton, And the centroids, if we're gonna base it here, start here to 2.67, so somewhat here, because it's the half of 4 is 2, then it's something located here. So after that, we're going to draw its we're going to draw a free body diagram. So the free body diagram will be now look like this. So as we can see, we solve the force in this loading, so we'll get a 140 kilonewton, so this, and we'll put it in its centroid, so we get a centroid of 3.5. so from here we move 3.5 meters, so here it is a 3.5, so we place this force of uniform load here, while also the uniform varying load, we get a 140 kilonewton force, and we find that its centroid is located 2.67 if we start from point C. So here it has a distance of 2.67 from point C. So as you can see, we have two unknowns. So to solve these unknowns, we will gonna do a moment and also a summation of forces. So to solve for the RC, we're going to do a moment at point B. So summation of moment at point B is equal to 0. So we're going to assign, if it is counterclockwise, it is placed on the left side, and if it is a clockwise, it is placed on the right side. So if we moment at point B, so the counterclockwise forces will be this. So moment is force times distance, which the distance, it must be perpendicular to that force. So this 50 kilonewton force going downward, it has a rotation of counterclockwise, so 50 times 1. And also this force RC, it has a rotation of a counterclockwise, so plus RC, which it has a distance of 7 meters. So that's it for the counterclockwise, is equal, so to get the so clockwise, so at point B, so this force going downward, so it has a rotation of clockwise, so 140 times the distance is 3.5 plus also this force is a rotation of clockwise, I mean, so it has a 140 times the distance from here to here is 7, then here to this force is 2.67, so if we add it, is 7 plus 2.67 is 9.67. So after that, we're going to get this unknown RC. So RC will be now here, we transpose it to the other side, so it gonna be 143.5 plus 149.67. 50 times 1 is 50, then since it's positive, if we transpose it to the other side, it's gonna be negative 50. And also we divide it by 7 so that the RC will be left alone, so 7. So if we calculate this, so we were going to have a RC of 256.26, since the unit of this is in kilonewton. So this is the RC now. So to solve the RB, we're going to do a summation of forces. So summation of forces vertical is equal to 0. So we assume that the summation of forces that goes upward is placed on the left side, while on the summation of forces and this as a direction of downward is placed on the right side. So what are the forces? So force is upward, so we have 2, so RB plus RC is equal to forces downward. We have 3 forces downward, so 50 plus 140 plus 140. So since we have a value of the RC, so we can now solve the RB. So RB will be now 50 plus 140 plus 140. Then RC, positive RC, transpose to other side, negative RC is 256.26. So if you calculate this one, so we will get a 73.74. A unit is kilonewton since it's force. So this is our reaction forces. RC, reaction forces in this one, RB's in this one. So since we get their reaction forces, we get the reaction forces on RB and RC, what we're going to do next is we solve their moment and shear in each segment. So at segment AB here, so we draw we cut the segment AB, so this is the point A, and there is a force applying at point A, 50 kilonewton. Then we let the distance from A to the cutted as X. So the shear AB will be, since it's since it's downward, so negative 50 kilonewton. Well, to get the moment at segment AB, it will become downward, so negative 50, then times the distance, 50x kilonewton. So that's the segment at AB. So next is we solve for the we get the total forces, summation of forces at B. So we draw it again from A to B. So there is a 50 kilonewton applying downward, and here there is a RB, which is 73.74 kilonewton here. So so to solve for the shear at B, since downward negative 50, upward positive, so 73.74. So negative 50 plus 73.74, so it is a 23.74 kilonewton. So VB will be 23.74 kilonewton. So after that, we solve the shear and moment at segment B and C. So at segment BC, so we draw this is the B, and there is a uniform load here. And it has a 20 kilonewton per meter. the uniform load. And since our VB is located here, VB, since it's positive, we draw it force upward 23.74 kilonewton. So this is our segment BC, and from B to the dotted line, we let it as distance x. So to solve for the shear at BC, there is a force upward 23.74, then uniform load is downward, so negative. Then to get the force of this uniform load is we get the area, so we have a length of x and a height of 20, so it will be written as 23.74 minus 20x kilonewton VBC. So it's shear at BC. And to get the moment at BC, we moment here, so it's upward, so positive to 3.74 times the distance from B to the dotted is x, then downward is negative, so the force here is this one, negative 20x. Since it is uniform varying load, we will solve its centroid. So the centroid of this one is just a 1/2 times the distance, which is x, so therefore it's x over 2. So simplify, so it's 23.74 x minus 20 over 2, it's 10x times x squared. So the moment at BC will be this one. So next is we do the same here. We get the summation of shear at B here we get, but in this we solve for the summation of shear at point C. So we draw so that we will understand. It's B here, then C. So we copied this. It's 23.74 kilonewton, and this one is just this B to C, and also at C there is RC, or reaction at point C, so we also draw it to 56.26 kilonewton, and this uniform load is 20 kilonewton per meter. So to get the summation of shear at point C, it's 23 upward, so positive 74, then also the distance from B to C is 7 meter, as we can see here. B to C it's 7 meters. So, and to get the force in this uniform load, just the area, so since it's downward, so minus it's 20, area is height of times distance, so 7. So and also a reaction force here that goes upward, so it's since upward, so plus 256.26. So to calculate this one, it is a 140 kilonewton VC. So after getting the VC, we will solve the shear and moment at point CD. So at segment CD, we draw so this is C, and since it is the shear at VC is 140, so positive, the force goes upward, so 140 kilonewton. And the load type of load here is uniform varying, which has a shape of a triangle. And also the distance from C to the cutted line is, we let it as X, and since it is cutted, kung ato ni padayon, di ba, it's the original shape is like this one. From C to D, it has a distance of 4 meters. And the height of this one is 70 kilonewton per meter. So since we cut the segment, so we need to find the value of this one, so we let this as Y. So to solve for the Y, so it is just the height of the original divided by the length of the original is equal to the Y over X. So it is written as 70 original over length, so original is equal to Y over X. So to solve for the Y, it's now just multiply both sides by X, so it will be cancel, so Y 70 over 4 X, and 70 over 4 is 17.5 X, so Y. So this time we'll now have the value of Y, so we can solve for its shear at segment CD. So shear at CD, we have a force of 140 upward, so positive, and uniform varying load downward, so negative, since it's triangle. So area of the triangle is 1/2, base is X, then height is Y. So we have a value of Y here, so we just substitute it, so 140 minus 1/2, then X, then Y is 17.5 X, so it is now 140, and 1/2 divided by 17.5 is 8.75, then X times X is X squared. So this is now our shear at CD. So after that, we will solve now its a moment at CD. To solve for the moment at CD, we're going to in this portion. So 140 forces is upward, so positive. Then the distance, perpendicular distance from here is x. Then the force is of this one is this, so just copy it, negative 8.75 x squared. Then to find its centroid, so we moment at point here man. So if we are basing here the centroids of a triangle, if we start at this part, so we just multiply it by 1/3 of its length, so length is x. So simplify, so 140x 8.75 divided by 3, so we will get a 35/12. Then x squared times x is x cubed. So this will be now our moment at CD. So since we already get the shear at each segment, this VAB, segment AB is negative 50 kN. Then sa segment sa BC, the shear function will be now 23.74 minus 20x. Then in CD, 140 minus 8.75 x squared. So what we're going to do is we plot, and as you can see here, since VAB is negative 50 only, so it's just, if you plot it, it's just a straight line from A to B, but it's in negative 50, so it's negative 20, negative 40, so the negative 60, so it's half of that. So negative 50, straight line to B, line B. Then in BC, since it's a function, we have a variable of x. So since the distance from B to C is 7 meter, so we put a number of 0 to 7 at x. So if x is 0, we substitute the x at VBC. If x is 0, it's 23.74. so B to C, so this is the distance 0 from B to C, so it's 23.74, so this is 20, so above 20 is 23.74, so this is 1. Then if x is 1, it's 3.74, so x is 1, so 3.74, so it's located here. Then if x is 2, it's negative 16.26, so negative 20, so it's located here. Then x of 3, negative 36. Then if x is 4, it's negative 56, so it is 1. Then until x is 7, it's negative 116.26, so 100, then 116 now, so it's located here. So that's the graph of shear at BC. So next is we graph for shear at CD. So we have a function of 140 minus 8.75 x squared. So since the distance from C to D is 4 meters, we substitute the x from 0 to 4. So if x is 0, so 140 minus 8.75 times 0 raised to 2, it will be just 140. So from C to D, so the distance 0 is located here, but since x is 0 and the value is 140, so 140 This is the 140 at 140. So the point is located here. Then if x is 1, it's 131.25. So if x is 1, 131.25 is this. If we trace it back to this part, then if x is 2, 105. So 1 2, so this one 105. And if x is 3, it's 61.25. so 60. So it's somewhat located here. And if x is 0, so we'll get a 0 also. If x is 4, we get a 0. So 1 2 3 4, so x is 4, then we get the value of 0. So this will be now the shear diagram. So as you can see, from B to C, since it's a first degree, it's just a straight line. Then from C to D is a second degree. So second degree is a curve 1. So as you can see, it is a curve 1 also. So this is a right shear diagram. So for the moment diagram, so since we solve the moment in each segment, so we have moment at A to B is negative 50x. Then moment from B to C, 23.74x minus 10x squared. Then moment from C to D, it's a 140x minus 35 over 12x cubed. So what we're going to do here is it's the same what we do in the shear diagram. So since MAB is negative 50x, so and from A to B, has a distance of 1 meter. So we let x 0 to 1. So if x is 0, it is also 0. Then if x is 0.5, it's negative 25. Then x is 1, it's negative 50. So if we plot this, so if x is 0 here, AB, as you can see, it's also 0. Then if x is negative 5, so this is negative 5. And the range of this is by 50. So 50, negative 50. So half of negative 50 is negative 25. So here, so if you trace, it's located here. Then if x is 1, negative 50. So it's here, located here. Then for moment BC, we have this function. So since BC is 7 meters, so we do the same. We let solve x from 0 to 7, just input them. So if x is 0, as you can see, it's also 0. So from BC, so distance 0 is located here. Then if x is 1, it's 13.74. So if x is 1, so it's somewhat located here. Then if x is 2 is 7, so it's lower. Then if x is 3 is negative 18.78, so somewhat here. Then x is 4, this one, it's negative 65.04, so somewhat here. Then if x is 5, this one 5, it's negative 131.3. Then if x is 6, it's negative 217.56. Then here, this one. Then if x is 7, it's negative 323.82. So 300, then 323.82. So it's located here. Then for moment CD, let's just do the same, and CD is the distance of 4 meters, so we let x as to from 0 to 4. So 0 to 4, so if is 0, then it's also 0. So from the distance 0 here is located here from C to D. If x is 1, so it's 137. So here, then if x is 2, is 256.67, so 256, so 250, so it's somewhat here to 56. Then if x is 3, this here, then it's 341, 300 and 350, lowers to 350, so this. And if x is 4, it's 373.33. So x is 4, 1, 2, 3, 4. So this, it's 373.33. 400. Lower of 400 is 373. So we have shown it's located here. So this is the moment diagram.